Yeah, today's going to focus a lot on the Young's double-slit experiment. But first, before we get to that, we have to understand what diffraction is. Okay, so I have a video to start us off here. So, videos, I think it's this one. Yeah. So essentially, diffraction is defined as the bending and spreading of a wave when it passes through an opening. Okay, so when a wave, let's say a water wave, or as we'll see towards the end of class today, when a light wave passes through an opening, it doesn't just go straight through the opening. What happens is it goes through the opening and it spreads out. Okay, so here's an example of a wave passing through a slit. Right, and as you can see, when it passes through the slit, it doesn't just go straight through the slit. It actually goes through, but it gets sort of deflected, right? It tends to spread out after it passes through the slit. Okay. Now, when the width of the slit gets smaller, you can see that spreading, that deflection is even greater, right? So it seems like there's some sort of relationship between the width of this gap here and the spread of the waves, or the diffraction of the waves. Okay, and so this is a new phenomenon. I know, at least I think it should be new. I know in grade 10, no one, or you guys don't talk about diffraction at all, the spreading of waves. So today should be kind of a new concept. All right. Okay, so let's pause this. We'll go back to this. Okay, so I took some snapshots here. Of that video there. All right, so a few things to note, just really quickly here. Oops, don't have actually on my notes here. Back to here. There we go. Okay, so a couple things to note. When the width of the opening is greater than the wavelength, there's actually not as much diffraction. Okay, so when that width spacing, when that slit spacing is quite large, there isn't as much diffraction. Okay, as the width is decreased, the wave actually experiences more diffraction. Okay, so there's more bending as the width of the opening gets smaller. Okay, now in brackets here, I indicate that really what we're focusing on here is the ratio between the wavelength and the width of the spacing. Okay, so as that ratio gets closer to 1, essentially the diffraction experienced by the wave becomes greater. Okay? So really, to determine how much diffraction there will be, we're kind of focusing on this lambda over W ratio. Okay? The ratio of the wavelength to the spacing of the opening. All right? Now, there's not a lot of calculations here, but I did put one example in. So let's consider two scenarios really quickly. In scenario A, we have a wave with a wavelength of 0.5 centimeters, and that wave is incident on a slit, and that slit has a width of 2 centimeters. Okay, so if we first tackle scenario A, when we calculate the ratio of the wavelength over the slit spacing, so that is 0.5 centimeters over 2 centimeters, we notice a ratio of 0.25, right? Of 1/4. Okay. Now let's do the exact same thing. Essentially, this 0.25 is a sort of measure of how much diffraction or bending, right? Bending. The light, or the wave will experience. Wave will experience. So when this number gets closer to 1, essentially it means that the wave will experience more diffraction. Okay, so let's take a look at scenario B. So we have again, let's look at this lambda over W ratio. When we do it for scenario B, the wavelength for the second experiment is 0.5, and the width is still, or the width has been reduced to 0.5. Okay, so we have 0.5 centimeters over 0.5 centimeters. And so the ratio here is just 1, right? And so this wave, essentially, the wave B, therefore wave B, will experience more diffraction than wave A. Okay? So essentially this ratio between the wavelength of the incoming wave and the spacing of the gap that the wave is allowed to pass through, that tells us how much diffraction we're going to get. Okay? When this ratio is very small, there will be very little diffraction. When this ratio increases, there will be more diffraction. Okay? Okay. Any... Okay, so on to something that you guys would have presumably talked about in grade 11 physics. Everyone's heard of interference before, I would assume. So when two waves are interacting with each other, they will interfere. Okay, so interference is just the phenomenon that occurs when two waves that are present within a given medium interact. Okay, now there's two types of interference. There is constructive interference, and constructive interference occurs when the two interfering waves have Okay, so here we have constructive interference. So we have two interfering waves, and what we notice in this drawing here is that the crests actually match up with the crests. And so when they overlap with each other, the amplitude of the wave gets larger, okay? It's kind of it's an additive effect. There's constructive interference happening. Similarly, we notice that the troughs match up with the troughs, right? So again, we have constructive interference. Okay, the amplitudes just add up with each other. This should all be review of grade 11. You definitely should have covered this in grade 11. Okay. On the other hand, destructive interference occurs when essentially the two waves are out of phase with each other, right? So when you have two waves passing through each other, you will have a crest, say, meet up with a trough. And so what ends up happening there is that the two waves just sort of cancel each other out, right? So again, when we look at this image, we see, oh, we have a crest matching up with a crest. Or sorry, a crest matching up with a trough. Now, when those two overlap with each other, the positive amplitude of the one wave adds the negative amplitude of the other wave, and you just get them to perfectly cancel out with each other. So you get perfect cancellation of the waves, right? Similarly, the trough of the first wave meets with the crest of the second wave. Again, you have perfect cancellation. So the resultant wave just has no amplitude whatsoever when you're in destructive interference, okay? Perfectly cancels out, all right? Okay, now in order for interference to occur, essentially we have to have the following checklist, the following criteria. And again, we'll kind of come, the reason why we're introducing this now is because it's a lot easier to understand it when we're dealing with like a water wave situation, okay? But what we're going to notice is that this same set of criteria here is going to also be present when we talk about the Young slit experiment, okay? And so we're kind of building up to showing that light will behave in a similar way. So essentially, in order for interference to occur, we have to have two or more waves that are moving through different regions of space from the source to the point of interest. So the source here is what is generating the wave, right? So we have something generating the wave or multiple sources generating a wave. And essentially, those two sources, the waves produced by those two sources will meet at a certain point, okay? Or they will meet at some place on their way to a certain point, all right? So the waves do come together at a common point, okay? And in order for this interference pattern to develop, these waves have to have the same frequency, okay? And the relationship between the two phases are such that the phase difference between the two waves is a constant, okay? So what this means is that the two waves are coherent with each other, all right? Now, I wish we had some sort of, like, we could go down to the lake and kind of play around with this, but unfortunately, we kind of can't, obviously. However, I have a video coming up towards the end of this where the guy actually does an experiment where he's generating two wave patterns in a little creek, okay? So we'll actually see this come about. But in order to study these interference patterns, we often use what's called a ripple tank. Okay, now a ripple tank consists of 2 point sources. Okay, so the 2 point sources are down here in the picture. So we have we label them S1 and S2. Okay, now S1 and S2 are basically just, you can imagine them, again, we'll see in the video, they're just two objects that are oscillating, and when they oscillate in the water, they generate two wave patterns. Okay, so essentially these two objects are oscillating up and down, and they will cause a pattern to propagate out into the in this case the ripple tank, right? Now the pattern produced looks like this. Okay, now this is a fairly complex pattern, but there are some main takeaways here. Okay, so all of the red lines indicate areas of constructive interference. Okay, constructive interference. All right. All of the blue lines indicate regions of destructive interference. Okay. And so essentially, if we were to look at this as it's happening, like in a ripple tank or in a creek or a river, as we'll see towards the end of class, what we would see is in the zones of constructive interference, we would see some pretty big crests and troughs, right? We would see a pretty oscillatory motion along the red lines, okay? But when we look at the blue lines, we would essentially see just like calm water, still water, which is kind of interesting, okay? So this sort of pattern develops because we have 2 point sources that are generating waves, and then those waves are hitting each other at different places and interfering in a different way, okay? Okay, I'll pause for a second here. right?
Where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up.
So Costa, to answer your question, it's pretty I would say it's pretty definitive, right? Like it's pretty clear. You get very clear distinctions between the zones of constructive interference and the zones of destructive interference. But yeah, you are right. There is a sort of gradation from one to the other, but it is pretty clear. So there's a lot of mathematics behind this picture. Okay, actually, before we get into the mathematics, let's introduce just a couple more things. So the blue circles in the previous page, I'll show you that again. So all these blue circles, the places along the zones of destructive interference, those are called nodes. Okay. Now, nodes are points along a standing wave pattern, which you should have learned all about in grade 11, where the waves that are produced, essentially the waves produce zero displacement. Okay, the red circles in the picture are referred to as antinodes. Now, antinodes is where the maximum displacement is observed. Okay, the blue lines in the above figure. The lines on which all the nodes fall along are called nodal lines. Okay, so nodal lines are lines, a line or a curve along which we have destructive interference the whole way along the curve. Okay, so all along this blue line here, we're going to have a zone of total destructive interference. So there's no peaks, there's no troughs, there's nothing like that. Okay. Okay, so there's quite a few definitions there. And then here's the picture that we're going to kind of focus on for a lot of today. Now, this picture is complicated, okay? But let's kind of step through it. So at the bottom here, we have S1 and S2, okay? Those are our two sources, all right? So going back to the picture, those green kind of balls that he was oscillating in the water there, those are S1 and S2, okay? PN is just some point along the nth nodal line. Okay, so in this pattern we have a whole bunch of different nodal lines and they're kind of spaced apart from each other. Okay, now PN is just some point on one of those nodal lines. All right, we have the angle that the nodal line makes with the perpendicular bisector. Right, that angle is is just measured from basically the center of our pattern out to the nodal line. Okay. L measures the distance from the middle of the two sources. Okay, so right in between the two sources. L measures the distance from that to our point that we're selecting. XN represents the distance from the point to the perpendicular bisector. Okay. And then the last two values here, I know this is a lot of info here, but PN S1 and PN S2, that's just those are called path lengths, okay? And path lengths measure the distance from the source to the point on the nodal line that we're interested in, okay? Now, I know this is kind of a lot of just, okay, you have this picture, what's going on with it? What's the point with it, right? So it turns out that we have a lot of cool mathematical relationships that we can develop from all of these quantities, okay? And so essentially, this is the picture that you want to have in mind as you're going through these problems. What we're going to be using is we're going to be focusing more on these formulas down here, okay? Okay, so yeah, let's see how this is done in practice, because I think it'll be a lot better once we kind of just get into it a little bit, okay? So we have all of these formulas. Essentially, this relates, so this value here is called the path length difference. Path length difference. Difference, okay. And it turns out that the path length difference is a half wavelength multiple of the wavelength. Okay, so it's some sort of half integer multiple of whatever the wavelength is of these waves. Okay, so that's a really neat relationship. It also turns out that we can do a little bit of trig and figure out a relationship between either the angle at which the nodal line is spaced at, or the distance from the nodal line to the center of our pattern. Okay. So I know there's a lot going on here, but I'd say let's do a couple of examples and we'll see if all of this kind of makes sense here. Okay. Okay. All right, let's get to it. So here's an example straight out of the textbook. Here it says the distance from the right bisector. So I'm actually going to draw out a picture similar to what I had up here. Okay. So the distance from the right bisector. So here I have 2 point sources, say S1 and S2. And I have a point on the second nodal line. Okay, so I have a nodal line that's doing something like this. And I have a point that I'm interested in on that second nodal line. Okay, so I'm going to call this point P2. All right. Now, in this question, I am told that the distance from the right bisector, oh, I guess point P. I'll call it point P, sorry. Distance from the right bisector to a point P on the second nodal line in a 2-point interference pattern is 4 centimeters. All right, so this distance here is 4 centimeters. I'm going to call that x2 is 4 centimeters. Okay. I'm also told that the distance from the midpoint between the two sources, which are 0.5 centimeters apart, 2 point P is 14 centimeters. Okay, so I have the distance from the midpoint between the two sources out to the point P. This I'm going to call L, and L is 14 centimeters. So 14 centimeters. I'm also told that the two sources are spaced, two sources which are 0.5 centimeters apart. Okay, so the distance between my two sources, I'm going to call that D, is 0.5 centimeters. Okay. So I have all of this information that's being given to me here. All right. My goal for part A here, I'm going to calculate what theta 2 is, right? So theta 2 is just the angle, between my perpendicular bisector, so the center of my pattern here, and the nodal line. Okay. So my first goal is to figure out what theta 2 is going to be. All right. So what I'm going to do is I'm going to go back up to these formulas and I'm going to find one that kind of satisfies all of these values here. Okay. So I'm interested in, actually, do I know what the So sine theta n is equal to xn over L. That's one formula, or that's the formula that I'm going to use for this first part. Okay, so sine theta 2 is equal to x2 over L. And I'm going to rearrange this thing for theta 2. So theta 2 is sine inverse of x2, which is 0.04 meters, over L, which is 0.14 meters. And I'm going to plug that in, and I get a value of approximately 17 degrees. Okay. So part A is good. For part B, we're actually looking for the wavelength. Okay, so the wavelength, I'm going to use my other formula for this, right? I'm going to use this formula right here. Okay, so sine theta n is a half integer multiple of the wavelength over the spacing between them. Okay, so sine theta n equals n minus a half times lambda over d. All right, and I know everything I need here, right? The only thing I don't know is lambda, so I can solve for that. So I'm going to rearrange this thing. So I get d sine theta n over n minus a half, okay, equals lambda. All right. Now in this case, my n value, because I'm on the second nodal line, my n value is equal to 2, right? N is equal to 2 because I'm on my second nodal line, all right? So coming back to this formula here, I can plug in all the things, right? So d is 0.5 centimeters, so that's 0.005 meters. Sine of theta n, so that's the value that I found in part A, that's 17 degrees, over n, which is 2, so 2 minus a half, which is equal to lambda. Okay, so my wavelength, plug that in, see what I get. (0.05 sine 17 over 1.5). Actually, wait, am I doing this right? I think I am. But I don't appear to be getting the right answer. I think I did something wrong here. Give me a second. Oh, I'm not going to use this formula. Hold on one second here. Yeah, so there's a lot of formulas involved here, and knowing... So one thing that I didn't use at all here was I didn't use the fact that the spacing between, or the distance between my midpoint to my point on my nodal line was L, okay? So let's back it up here. Back it up a second. Sorry. Let's retry that one. Okay, one more example for this stuff. So we have two identical point sources, and those point sources are 5 centimeters apart. Okay, so my D value is 0.05 meters. They are in phase, which is good. That means we're generating coherent waves. And they're vibrating at a frequency of 12 hertz. So we're actually told the frequency of these waves. Okay, so frequency is 12 hertz. They produce an interference pattern when they're vibrating. Here we're told that a point on the first nodal line is 5 centimeters from one source and 5.5 centimeters from the other. Okay, so let's draw a picture about what's happening here. All right, so we have our two sources, S1 and S2, and those sources are 0.05 meters away from each other. We're looking at a point on the first nodal line. So here's our point P, and that point is, we'll maybe call it P1. That point is 5.5 centimeters away from one source and only 5 centimeters away from the other source. Okay. So the way that I'm going to call that, again, if you go back up to the picture that I had way up here, really what I'm being told here is I'm being told I have P1 S1 and P1 S2. Those are the two quantities that I'm being told in this question. All right. So coming down here, I'm told that P1 S1 is 5.5 centimeters, so 0.055 meters. P1 S1 just represents the distance between the point and the source. Okay. And P1 S2 is 5 centimeters, so 0.05 meters. Okay. And so what I'm going to use here, I'm going to use the formula that I have for the path difference. Okay, so coming all the way back up to here, I'm told that the path length difference between the 2 points is equal to n minus a half times lambda. Okay, so I'm going to be using this formula right here. All right. So I have P1 S1 minus P2, or P1 S2, is equal to n minus a half times lambda. All right. I am told that this point lies along the first nodal line. Okay, so what that tells me is that n is equal to 1. Okay, and now I have everything I need to figure out what my wavelength is. Okay, I have all my quantities that I have that I need. Okay, so P1 S1, that's 0.055 minus 0.05 equals 1 minus a half times lambda. I'm just going to rearrange this for lambda. So the wavelength is 0.055 minus 0.05 over 0.5. Let's see what we get. I get a value of 0.01 meters. Okay. So I've successfully found the wavelength of the waves being generated by these two point sources. Okay. Alrighty, so on to Young's double-slit experiment. Okay, so I would say this is a pretty interesting experiment, and it really highlights why light is treated as a wave. Okay, now I'm actually going to go back to that video that I was showing a second ago. Does anyone watch Veritasium's videos by any chance? They're pretty great, I would say. They're pretty awesome. Okay, so I'm going to mute my microphone, and I'm going to pause it at a certain point, and then we'll discuss, okay?
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's Double-Slit Experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch
in breadth,
and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes.
smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you could take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm gonna place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we gonna see on the bottom
Well,
of
the
the
obvious
box?
thing you think you're going to see is you're going to see two lines.
Okay, I have a question for you guys. So we have the light shining on this box, and on the very top of this box, there's a little piece of cardboard, and on that piece of cardboard, there's two little vertical lines, two parallel slits that are kind of etched in the top of the piece of cardboard, okay? Now, these people are about to look inside the box and see something on the bottom of the box. Jana, I have a question for you. What do you expect we'll see in the bottom of the box?
lines on the bottom of the box.
2 bright bands.
2 little lines.
I think,
yeah.
I think it'll be one line instead of 2.
I can expect to see the whole box lit up.
It'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots. How many?
It's one circle.
Well, there's one in the middle strongest, 2 either side.
The 2 on the outside are multicolored. The one in the middle is just white.
It's kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
2 slits.
2 slits. That's incredible. But all we're doing is we're putting a light through 2 very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved now that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see 2 bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference.
Why is the stream suspended for policy violations?
Meets up with the trough from the other, then we get destructive interference.
Seriously?
Yeah, because we were watching. Yeah, I think so.
Wow, they're going after everyone, eh? I think we got the gist of it, though. No.
I just got banned.